Hi. Let us continue on our example. Let me briefly remind what we have. So we have two mutually exclusive events. Event A, person has a disease. Event A, complement, person doesn't have disease. And we have outcome B, which a person was tested and test was positive. So given this information and also our estimates of the prior probabilities, likelihood of outcome B given state of the world, we will update the conditional probability or posterior probability that person has a disease given test is positive. From the governmental agencies or from some research and review of the medical records, one could estimate what's the population of in that particular country, what is the percentage of population which has disease, and naturally what is the percentage of population doesn't have disease. In this case, the prior probability that percent of the population which has a disease is 1% or 0.01, and alternatively the percentage of the population which doesn't have disease is going to be 99% or 0.99. Also, through the experimental findings, we determine what is the probability that a test is signals as positive given that person has disease and given person doesn't have disease. So it came, these probabilities, conditional probabilities or likelihood of experimental outcome are equal respectively 0.95 and 0.01. Now, with all this information on prior probability and also on the likelihood of experimental outcome, we could update our posterior probability or conditional probability. What is the probability that person has a disease given test is positive. Probability B given A is 0.95. Probability that person population has a disease, the probability of disease in the population is 1%, and no disease is 99%. And naturally, if a random person is tested, then its chances that it has a disease is 0.01. So we multiply 0.95 by 0.01 in numerator. In denominator, we substitute the values for PBA given A times PA plus PB given A complement times PA complement. Substitute those values and we received at the end 0.49. So given that test is positive, the probability that person has a disease is almost 50%. So on its own, a random person when pulled from the population has only 1% of chance that he has a disease. But with some additional information on the given experimental outcome. We update our posterior probability and obtain a knowledge that the person has given that test is positive, the person is likely to have 49% of chance to be to have that disease. Okay, I hope this makes sense, and there is no particular assignment on the Bayes probability theorem, but it's very useful concept, and if you search the literature, there's a widespread application of Bayes theorem in many fields, and the field I'm coming from, medical device, so FDA is certainly is on board that Bayes theorem is findings of the Bayes theorem is being utilized in medical device industry, in clinical studies, or in just design of the product. Okay, then see you in the next section where we're gonna talk about decision theory. Okay, see you.